and you differentiate that with respect to r, what does it give you? It gives you, good grief, come on. I would definitely take a point off your test for this. So I'm sure some of you experienced this, right? That's supposed to be an x, obviously. So -1 from this lecture, for sure. So x e to the rx. This is why we need sabbaticals. But anyway, sabbaticals is like extended period of time you have to fix all your mistakes. It's a magical idea. But anyway, we always teach. So no fixing mistakes. Just go on. Partial r of x to the r. Well, that would be log x times x to the r. And of course, these are the repeated, these are the, again, putting x there. These are the solutions in the case that the characteristic root's repeated, right? So here's like a little general derivation for why this is working. If I have a linear differential, linear differential equation, all right, something like, let's see here. Suppose I have, I need to start this in the right place here. Come on. Let's see here. So suppose, let's just focus on this calculation. Suppose that y of lambda x is a solution, all right? Here's an indication of why the derivative with respect to lambda of that is also a solution after you put lambda equal to lambda 1. So I'm supposing that y lambda 1x is a solution to some problem, okay? And so if we take L of this, if we're allowed to commute the partial derivative with respect to lambda and the differentiation in the linear operator which defines the differential equation, if you could change those around, then that will give us partial lambda of this. But if the solution has a repeated root, then that means I can write this as like lambda minus lambda 1 squared e to lambda x, right? So apparently I'm in the constant coefficient case in this derivation right here. So that gives me that. But differentiating with respect to lambda gives me 2 times lambda minus lambda 1 plus that, right? And when I put lambda equal to lambda 1, well, this piece is 0 and that piece is 0, so I get 0 again. This is sort of the this is the details of why it works out in the constant coefficient case. But essentially, this is the idea, is that if you have a characteristic value, you can commute L and partial lambda. And when you do that, it will give you that the you're just differentiating something which is going to be 0 after you plug it in. I don't know. This is not convincing to me either. I'm sorry, guys. It seemed good when I read it before class. But, you know, sometimes we trick ourselves. But anyway, that is actually something, that is a general solution technique, that if we have a solution that has some characteristic value, right, that, like the initial value, the exponents here, if we have a repeated exponent, we can differentiate with respect to the exponent. It will generate a new solution. That is, in fact, something that's true, even if I haven't made a convincing argument for why it's true today. And so when you apply that to the Frobenius solution, something really beautiful happens. See, so our general solution, Frobenius solution, looks like this, actually. So we have x to the n plus r. I just pulled out the x to the r out front. And if you think about it, the coefficients have an r dependence, don't they? I mean, that's been explicit in the star equations I've derived today. So if we wanted to find what the solution looks like for repeated Frobenius solution, we should really take our Frobenius solution and differentiate with respect to the exponent. Doing so gives me this. Now, so I got log x, x to the r, plus this, times this Frobenius solution, and then plus x to the r, sum n equals 0 of the derivative of those coefficients with respect to r, Frobenius solution. So what this means is that if you have the first solution to a repeated exponent case, right, you can derive the second from this formula. But it's not just a simple matter of multiplying by log x usually, all right? Usually you have to add together the series you already have times log plus something related to the derivatives of the coefficients to get the other piece. This is a little bit more exotic than the Cauchy-Euler problem, right? But there it is. I mean, this is a stone cold formula for the solution in the repeated root case. All right. So you can hit the lights again, King. So you guys, I don't think I assigned you one. If I did, it's accidental. I don't believe I did. If you look in your textbook on, I'll find it eventually. So we've been in section 8.6 today, primarily. And if you look in section 8.6, he eventually gives you this big old block of text called method of Frobenius. And on page 467, this is method of Frobenius. I will read it for you. So to derive the series solution about a singular point x naught, so like part A, he says, assume it's a regular singular point. Great, all right? And then he says, you basically assume that the solution has the form an times x minus x naught to the n plus r. That was our starting point. Great. And then using term-by-term differentiation, you substitute the Frobenius solution into the equation that you're given, and that it gives you a recurrence relation in the coefficients of the Frobenius solution. That's what we've been doing. Great. And this is basically you plug it in, you work it out. And then part E, take r equal to r1, the larger root of the initial equation. So like when I got r equal to 0 and r equals to 2/3, I took his advice. I did the 2/3 one first, all right? And you use a relation obtained like my star equation. You solve for a1 and a2 recursively in terms of a sub naught and r. This is what we did. And then part F, a series expansion to 29 is obtained. Okay, so this method of Frobenius on page 467 just tells you how to find the first solution, all right? So, and he assumes that the initial equation has a real root. As we've seen, it doesn't have to. Frobenius' theorem on page 468 says that if you have a regular singular point, you find the Frobenius solution at the larger real root, then the series converges for all x such that x minus x naught is less than r and is greater than 0, where r is the distance from x naught to the nearest other singular point, real or complex. So there's an extension, the theorem I had at the start of the class about a regular, an ordinary point for a differential equation and how to find the domain. The same is kind of true for the Frobenius solution. The Frobenius solution will also work right up until the next singular point for the problem. So for our Cauchy-Euler problem, we got solutions that work from 0 to infinity because there was no other singular point except for 0. If you did have another singular point at like 5, if like 0 was a regular singular point and 5 was just an honest, just ordinary singular, it's an unfortunate turn of phrase. If 5 was a irregular singular point, or regular, I don't care, whatever, singular, then the Frobenius solution, I won't want to really say based at 5. I don't want to say centered at 5, because the Frobenius solution's not centered at 5. It will exist from 0 over to 5. If you have a Frobenius solution at 0, what the theorem says. So if 0 is a regular singular point, and if I have like 5 as a singular point, then the Frobenius solution will work in here. If you happen to have that minus 1 plus I was a singular point, then over here, if I built a Frobenius solution for negative x, it would work like here, minus root 2 to 0. It would work over there. It's up to the nearest singular point, so just like we did at the start. But I don't know, I never ask you guys questions about this. But that's theorem 6 in section 8.6. Then in 8.7, here it is. 8.7, theorem 7, you see how horrible it really is. 8.7, theorem 7, he discusses, and here's where it gets weird. If the exponents do not differ, all right? The exponents are the solutions to this, right? R1 minus R2 so if you have solutions R1 and R2 are exponents, all right? That is, they solve this. So suppose they solve the initial equation, all right? Then there's cases. Number one, if R1 minus R2 is not an integer. So if the difference is not plus or minus 1, 0, plus or minus 2, any of those, right? Then what you do is you just do the Frobenius method 2 times. And each separate exponent will yield you a solution. Okay? That would be like 0 and 2/3. Works out like that. The first example I did. That's part A. So here I'm talking about theorem 7 of section 8.7. Part B, if they're equal, if R1 equals to R2, then he says you find a Frobenius solution, and then the other one is given by, he says, y1 is equal to, you know, the sum an x to the n plus r, and then y2 is equal to, he says, y1 log x plus the sum n equals 1 to infinity of bn x to the n plus r. He's got it centered at a different point other than 0, but I'm writing it centered at 0. I hope that's okay. I just showed you better than this in my notes. I showed you that these b sub n's, they're not just any b sub n's. They're the ones that are obtained from differentiating the coefficients for your y1. So this is an improvement on his theorem 7. It's not mine, by the way. I found this in a book by Rabenstein, which is a beautiful, deeper book on differential equations that used to be used for this course. Not this course per se, but So you might wonder then, see, what if R1 minus R2 is in the integers? What if the difference of the exponents is an integer? Well, he describes that in equation 16, what you do. It brings a logarithm in. It's much like the case that is repeated, actually. But the truth of the matter is, there's still a case 4. What's case 4? Or a D? Complex, right? So there's actually 4 distinct solutions to the Frobenius solution, right? And I've shown you examples of every one of these cases today, except for the case that R1 minus R2 differs by an integer, right? So I hope I've showed you enough that you can try the problems for yourself. There's 1 or 2 of them in your homework, I think. Maybe, I forget exactly. But they're not, they take some time, but they're really just like the power series, all right? So don't be too scared of them. Just try them. Make sure you work with someone else, though. I mean, like, it's so important to check your work as you go on these, because if you make a mistake on your exponent, you pay a pretty large price if you keep doing. I mean, you really want to work out the star equation, as I called it, carefully in each one of these before you get too far into it. That's it. So next time, we will be onto the wild world of partial differential equations. So thanks.